After studying this module, you shall be able to know about different techniques for the study of kinetics of fast reactions, derive relaxation for temperature jump method, calculate the rate constant for temperature jump method. Introduction. Those reactions which carried out in short span of time, then the time required to mix up the reactants cannot be examined by conventional methods. Those reactions are known as fast reactions. For studying the kinetics of such reactions, powerful experimental techniques have been developed by the German chemist Manfred Eigen in 1950. In this module, we will emphasize on the various methods to study the kinetics of fast reactions. Let us see the methods to study the kinetics of fast reactions. The first method is relaxation method. Eigen and his co-workers used relaxation methods to examine fast reaction in solution. In these methods, the reaction system in equilibrium is exposed to an abrupt change in some physical parameter on which the equilibrium constant of the reaction depends. If the change is applied suddenly, there will be a time lag while the system modifies or relaxes towards new state of chemical equilibrium. This time lag, called relaxation time, it can be related to forward and reverse rate constant, which is then examined. Relaxation studies takes place with the parameters such as temperature, pressure and electric field. Figure shows the device for temperature jump method. There is a high voltage power supply that charges a capacitor C. On attaining a certain voltage, the spark gap G breaks down, discharging the capacitor and transferring a strong current over the cell, arranging the reactor system at equilibrium in a conducting aqueous solution. With the passage of current, the temperature of the system increases by about 10 degrees centigrade in a few microseconds in the equilibrium value suitable to the temperature jump. Consequently, the intensity of the light beam parting the cell and arriving the detector, that is the photomultiplier tube, is modified. The output of the photomultiplier tube is exhibited on the vertical axis of the oscilloscope. In this manner, the curve showing the variation of concentration versus time is presented on the oscilloscope screen. We shall now deduce expression for the rate constant of fast reaction. In case of displacement from equilibrium is very insignificant. The rate of relaxation, that is restoration of equilibrium, always follows first order kinetics. Consider a reversible first order reaction where A be the total concentration of reactant and the product A plus B and X be the concentration of B at any instant. Then R is equals to dx by dt, which is equals to K1 into A minus X minus K minus 1, that is the rate constant of reverse reaction, into X. If Xe is the equilibrium concentration, then delta X is equals to X minus Xe, or X is equals to delta X plus Xe. Since del of delta X by dt is equals to dx by dt, we have del of delta X by dt is equals to K1 A minus Xe minus delta X minus K of reverse reaction into Xe plus delta X. At equilibrium, dx by dt is equals to 0 and X is equals to Xe. Hence, from equation 1, we have K1 into A minus Xe is equals to K minus 1 Xe. Substituting this in equation 3, we have d of delta x by dt is equals to minus K1 plus K minus 1 into delta x is equals to minus Kr into delta x, where Kr is equals to the sum of both rate constants is the relaxation rate constant. Equation 5 can be integrated to give delta x is equals to delta x naught exponential minus Kr into T. The reciprocal of Kr is called the relaxation time tau, which is equals to 1 upon sum of K1 plus K minus 1, which is equals to 1 upon Kr. Let us now consider a somewhat more complicated case involving a first order forward reaction with a second order reverse reaction. It is the case when A is in equilibrium with B plus C, where small a is the total concentration and x be the concentration of B, which is equal to the concentration of C. Then the rate law is given by equation number 8. Now, delta x is equals to x minus xe, where xe is the equilibrium concentration. Hence, it reduces to equation number 9. At equilibrium, dx by dt is equals to 0 and hence x is equals to xe, or delta x is equals to 0. From this, equation number 9 reduces to equation 10. On substituting equation 10 in equation 9 and simplifying, we get equation 11. Assuming that delta x is very small, therefore k minus 2, which is the reverse rate constant, can be neglected with respect to first two terms, giving equation number 12, where Kr is equals to K1 plus twice of K minus 2 xe is the relaxation rate constant. Equation 12 can be integrated to give equation 13 and the relaxation time as equation 14. You can see in example 1. The relaxation time for the fast reaction is given as 10 microseconds and the equilibrium constant as 10 into 10 to the power of minus 3. You have to calculate the rate constant for the forward and the reverse reaction. On using equation 7, you can have the relation of tau and k. So, you can get the value of K1 as 10 to the power of 3 second inverse. Now we will see about the flow methods. The most popular flow method is the stop flow method. The diagram of its experimental setup is shown in figure. Two syringes A and B contains distinct reactant and are fixed with proper valves. The common drive mechanism D consists of an air-driven piston by which the solution is forced into the mixing chamber M. Another syringe on the right receives the effluent solution and is arranged so that when its plunger strikes a barrier, the flow is abruptly stopped. At the same instant, an oscilloscope is triggered to establish the time origin. The time scale is provided by the sweep frequency of the oscilloscope, which displays a plot of the transmitted light intensity against time. In this arrangement, the distance between the mixing region and the observation point P, that is the point at which the absorption of light is monitored, is small. The method of detection operates the UV visible spectrophotometer by determining the values of a suitable physical property as determined at several times after mixing with the aid of an appropriate technique. Kinetic data are obtained. Being less popular in the former methods, the continuous flow and quenched flow methods are also used, in which measurements are made at different distances from the flow tube, that is, at varying distances d. There is no utilization of stopping syringe. The principle of this procedure uses the information that the measurements along the flow stream amount in effect to determination at different times. With a known and a constant flow rate, the time corresponding to each reading is known. By placing several detectors alongside the tub or moving a single detector to different positions, the measurement can be made. There is a minor perfection in time resolution in the continuous flow method as compared with the stopped flow methods. As though the continuous flow method utilizes large quantities of solution, it is less usually used. In the quenched flow process, samples of the reaction mixture are quickly mixed with a quenching mixture, followed by the analytical determination that can be made at ease. Different samples can be having different timings by using different flow rates of different distances along the flow stream. This method is best appropriate to the study of exchange reactions which takes place too fast for the typical sampling techniques. Now we'll see the pulse method. Pulse method is also utilized for studying the fast reaction. Short pulse of electromagnetic radiation using light, ultraviolet radiation, X-rays or charged particles, usually electrons, start the reaction by creating very high concentration of excited state molecules. If a powerful flash of visible or UV radiation is utilized, the method is called flash photolysis, while on the other hand, from a generator charged particles are used, the method is known as pulse radiolysis. Flash photolysis. This method was pioneered by R.G.W. Norrish and G. Porter in 1949. The apparatus for flash photolysis studies is shown in figure. The sample is exposed to a very intense flash that have energy of the order of 10 to the power of 5 joules and duration of 10 microseconds. The flash is so powerful that in several cases about all the molecules of the sample are excited, due to which most of the molecules are broke into free radicals. Power of the order of 50 megawatt can be obtained for a few microseconds. In recent years, high-intense pulse laser light sources have been utilized in flash photolysis. The concentration of the intermediate formed by flash photolysis is followed as a function of time by absorption photometry. You can see the apparatus for flash photolysis. A condenser of high microfarad capacity is charged to 10,000 volts by a high voltage supply. Through the trigger signal, a spark is created in the spark gap which allows quick passage of current via the flash lamp. The condenser discharges in a few microseconds. The lasers can create a flash of the period of few nanoseconds. Immediately after the capacitor discharges, the flash lamp is spontaneously triggered off. The rate of the fading of excited molecules or free radical is followed by the rate of increase in the monochromatic transmitted light as calculated with an oscilloscope and photomultiplier. The spectrometer is fixed such that the light moving via the illuminated cell is of the wavelength that is absorbed by the excited molecule or free radical. This technique is known as kinetic spectroscopy. Norrish and Porter shared the 1967 Chemistry Nobel Prize for contribution to fast reaction kinetics by disturbing the equilibrium by means of very short pulses of energy. Flash photolysis has been used for deducing the absorption spectra of free radicals such as NH2, CH3 and ClO, whose concentration may be as small as 10 to the power of -6 molar. Pulse radiolysis. By utilizing pulse radiolysis, transient species can be generated by direct ionizing radiation. If a beam of high energy electrons imposes on water, quantities of stable and unstable species are generated. They start from the energy transmitted to water molecule by the electron beam. It is normal to express the amount of each species by a G value, which signifies the number of species formed per 100 electron volt of energy absorbed by water. The species made in the pulse radiolysis of water with the G value displayed as the coefficient of each species are given by equation 15. The first three are highly reactive entities. The hydrated electron and the hydrogen atom are strong reducing agents, and the hydroxyl radical is a very powerful oxidizing agent. In the absence of suitable scavengers, the species rapidly decay by the reactions of the following types. Due to these and various other reactions, selective practices have been developed to permit the study of each electron, hydroxyl radical and H radical distinctly. For instance, if it is required to study only electrons or use completely hydrate electrons to produce other species, one must work in neutral or basic solution to escape damage of electron by hydronium ion. The hydroxyl and H radical are often detached by shifting reactions such as those with formate ion or tertiary butyl alcohol, CO2 radical along with minus sign. The hydrogen atoms in alkaline solution are converted into hydrated electron, as you can see in equation 23. Now let us summarize. Various methods are there to study the kinetics of fast reactions, which include relaxation method, flow methods, pulse methods, flash photolysis and pulse radiolysis. Relaxation methods involve a sudden difference in some physical parameters such that the system moves to a new state of chemical equilibrium, and the rate of this change, called relaxation, is then examined. A flow method uses ultraviolet or visible spectrophotometer for the kinetic data. Pulse method utilizes a short pulse of electromagnetic radiation to produce excited state molecules. In flash photolysis, powerful flash of high energy is utilized to produce free radicals, and its concentration is examined as a function of time by absorption photometry. Pulse radiolysis exploits ionizing radiation for the production of stable and unstable species.